Hi everyone, my name is Andrew, and today I'll be going over the results of my Lab 5 for the Physics 2212. So the purpose of this lab is to basically model a physical and computational system exhibiting this concept called Faraday's law and compare the data that we collect from both of these systems. And the goal of this lab is to basically learn and observe Faraday's law and the underlying concepts that support this law, including flux, current, and EMFs. And so the results of this lab are that we successfully modeled the behavior of Faraday's law physically and computationally. And the times for the computational and physical models were the same. For the physical model, it was 1.376 seconds. And for the computational model, it was 1.378 seconds. So there are basically two fundamental principles that are associated with this lab. The first is Faraday's law. And Faraday's law is basically the law that states that if there is a changing magnetic field, then we would be able to produce a current that would also produce a magnetic field opposing that inputted magnetic field. And there's also this concept called magnetic flux, which is basically the amount of magnetic flux that floods through an area. And so there are a few assumptions that we made for this lab. The first assumption was that we assumed that the bar magnet acts as a magnetic dipole. We also assume that the system is isolated and that there's no other magnetic fields that could interfere with the experiment. And we also assume that the magnetometer app correctly defines the north pole of the magnet. And so the expectation that I had for this lab was that I just expected that the physical and computational models would be similar with small differences between the two models. So for modeling the system, we first marked the north pole of the magnet using the magnetometer app. We placed a tube of aluminum foil vertically and measured the length of the tube. We then recorded ourselves dropping this magnet through the tube with our phone, and we used to basically scrub through the video of our phone to find two times. So the first time that we found was when the magnet first enters the tube. The second time that we found was when the magnet exits the tube. And we basically calculated the amount of time that happens between these two events and repeated this 5 times to calculate the average time it takes for the magnet to fall through the tube. And so for the data that we collected from this experiment, we found that for the aluminum foil tube, the length of it was 0.3 meters, the width of it was 0.06, the inner radius of the tube was 0.017 meters, and the outer radius of the tube was 0.023 meters. For the magnet, we found that the mass was 0.018 kilograms, and the magnetic dipole moment was 2.118. For the time measurements, we basically, again, did 5 trials. We found for the first trial was 1.42 seconds, for the second it was 1.4 seconds, for the third it was 1.34 seconds, for the fourth it was 1.34 seconds, and for the last one it was 1.38 seconds. And then we got that the average time was 1.376 seconds. And we basically note that the magnet pretty much falls slower within the tube than in free space because the cylinder pretty much exerts an upward force opposing the change in flux. And so now we basically modeled this system computationally with closed scripts. And so for the first part of the code, we were basically inputting the data that we collected about the tube and the magnet, including like the width, the length, the inner radius, and the radius of the tube, as well as the mass and the magnetic dipole moment of the magnets. And we also set up methods for calculating the magnetic field of the bar magnet, as well as the change in flux or change in time for each ring of the tube. And so this code basically calculates the motions of the magnet falling through the tube, as well as calculating the currents that are produced from the falling magnet, as well as other information about updating the magnetic fields and all the other forces for the forces acting on the magnet, including like the gravitational force and the magnetic force. And so after we ran our code, we basically got this graph plotting the velocity of the magnet as well as the time between when the magnet enters the tube as well as when it exits the tube. And we basically see that in the output that the time it takes for the magnet to enter and exit the tube is 1.378 seconds. And so for interpreting the simulation, when we're looking at the tube, we see that there's coloring within the tube that pretty much indicates the currents that flows throughout each ring of the tube, with the colors being the different directions of the current. So the blue represents a clockwise rotation of the currents, and the red is a counterclockwise rotation of the currents. And we see that the blue is on top of the red currents. And this is kind of predicted by Lenz's law, which basically states that the magnetic field from induced current opposes the change in flux. And also, like, just to note, if we flip the magnet, it wouldn't really change anything. For the times for the computational physical models, we basically found that they were basically the same. The physical model was 1.376 seconds, and the computational model was 1.378 seconds. The shape of the velocity versus time plot kind of tells us that there exist multiple forces on the magnet, which in our case is the force of gravity and the opposing magnetic force. And there are a few possible sources of error. So one is just measurement error, so that we'd be like reading or recording the data. There could be equipment error, including like like phone recording not being accurate for the timestamps. And I guess like there could exist other magnetic fields, and that would pretty much interfere with the experiments. And so for the lab questions, for the first questions, I basically answered that we know that the resistivity is associated with the currents being inversely proportional. If the resistivity decreased to as close as possible to zero, then our current would be extremely high and cause the magnet to fall extremely slowly within the tube. And for the second question, we said that if there were holes or slots in the tube, there would be less current rings within the tube itself. Therefore, with less overall current rings, there will be less opposing force within the tube, and thus the magnet will fall faster within the tube. This would basically result in a shorter period of time where the magnet is falling within the tube.